Hey everyone. In this recording, what we're going to do is just go over basic logistic population growth. This is the main concept that we're going over in Lab 2. And so I just want to make sure that we have this concept totally down before you start working on the Lab 2 problems. So what we're going to start off with is just this blank whiteboard and just describe graphically what we mean by density dependence, right? We've done this in our lecture this past week as well. We looked at what we mean by density dependence, and we did something like this, where we said, okay, we have on the x-axis, we have abundance. On the y-axis, we have R, or the intrinsic rate of growth, but this time it's sort of a realized rate of growth, where we start off at low densities, where we have a really rapid growth, and that's R max, or I'm going to call it in this, just because I have trouble writing subscripts in this whiteboard, I'm going to call it R star. This is the maximum or optimal rate of growth for the population. And we'll start off there. And as density goes up, or here I could call this density, but it's easier to just write out N because it's hard to write in this whiteboard. But this is what we mean by density dependence. As density goes up, the rate of growth goes down, and at some point you're going to cross a critical threshold of 0 that is neither growing nor declining. And at that critical threshold, where you're neither growing or declining, that's an equilibrium point, and the abundance at that equilibrium is K, or carrying capacity. All right, so we've gone over that. What we're going to do in this mini lecture is just go over another way to look at density dependence. And this time, instead of thinking about the intrinsic rate of growth, R, what we're going to do is break that down into its subcomponents. Remember, R is equal to B minus D, or birth rate, per capita birth rate, minus the per capita death rate, is the rate of growth. All right, so let's think about B and D. And let's let both of those be density dependent. So we can let B equals, you have optimal birth rate, and then as density goes up, the birth rate goes down, and the population growth becomes slower and slower, or less and less favorable, and we can make this a linear model. So we have maximum birth rate minus some slope term times abundance or density, right? So this is density dependence, but it's on the birth rate. Now we can do the same thing with deaths. We can have, okay, we're going to start off at the optimal death rate. What is the optimal death rate? As low as possible, right? So death is actually going to increase. The death rate is going to increase with density, and we'll add a slope term times abundance or density. And so now we have both birth and death being density dependent. So this both of these equations represent density dependence. And I'll just say dense dep because it's hard to write in this whiteboard. So now we have two density dependent equations. Let's actually look at those equations graphically. So we'll stay with density here, and now I'm going to change this axis to vital rate, or VR, vital rate, and because we're considering both births and deaths. All right, so I'll draw the birth rate in green. So we'll start off at an optimal birth rate. I'll call it B star up here, and the birth rate's going to decline with density, like that. And the death rate I will make in red, and we'll start off at a minimal optimal death rate that is quite low. There we go. And we'll increase with density. All right. Now this is really the same thing as we looked at up here, because if you think about R, or realized R being the birth rate minus the death rate, if both the birth rate and the death rate are changing with density, R will also change with density. And if birth rate and death rate are changing linearly with density, R will also change linearly with density. All right. And so you can see that R is the difference between birth and death. So the difference is greatest at low abundance. So R is greatest, right? Birth minus death is a little bit smaller as density gets higher. And at some point, at this very important point here, birth rate and death rate are equal. And that point is, you guessed it, if you draw a line down to the abundance, that is carrying capacity, right where it meets. So this is an equilibrium point. It's really easy to see that it's an equilibrium point here because we don't even have to draw this zero line. We know that when birth and death are equal, that is, they cancel each other out, the population won't grow. So birth minus death is 0. That means we're at a point where there is no growth because the intrinsic rate of growth is 0 at that point. And so that is our equilibrium point, and that's why it is circled multiple times here, because it's a very important point. All right, so that's the graphics of density dependence. Now let's go over the mathematics. Yay! All right, let's think about this equation. Let's start from a very simple place. So what I'm going to start off with is the basic equation of exponential growth. Delta n is equal to r times n. All right. Now we can remember that r is equal to b minus d. So another way to write this is delta n is equal to b minus d in parenthesis times n. So far so good, right? So this is just our basic exponential growth. Now we're going to let both of these things be density dependent. B is going to be density dependent and d is going to be density dependent. So let's write that equation out, and we're going to have to use a little more space here. So I'm going to give myself a little more space here, and I'll zoom in, and hopefully you can still see what I'm doing. So I'm going to give myself a little more space, and I'm going to write out this equation. It's going to get a little messy, but try to follow along. And these equations are in the Gatelli book, so don't worry. You can watch this over again. You can read the Gatelli book, and hopefully this will all make sense. We're just going to do some basic algebra. That's all. All right, so delta n is equal to... let's write this out like this. So we have b is now b star minus an. So we'll say b star maximum birth rate minus an, right? Minus, and d is now d star plus cn. And all of that now, that's just the b minus d, right? All that times n. And this right there is our fleshed out equation, right? This is just this equation here fleshed out so that both b and d are density dependent. Okay, let's go a little farther. Now, what we're going to do next is we are going to rearrange this. So let's basically rewrite this in a very similar way, but slightly different. And here we go. We're going to say b star minus d star, right? That's the maximum birth rate minus the minimum death rate, our optimal death rate. Now we're going to take the other terms, and now we say minus an, right? And then we say minus cn, and then multiply that all by n. So I'm just rearranging the terms here, and we can do one more rearrangement, which will just be taking this n and factoring that out. So then we just have this is n times a plus c. Well, let me show you. It'll make more sense here. So delta n is equal to, and we can write this out as b star minus d star minus n times a plus c. All right. So we just factored that n out and then multiply that by n. Hopefully that made sense. So this is the same thing. So minus n times, in parenthesis, a plus c is just minus an minus cn. All right. So let's move on. And the next step is what we're going to do is we're going to multiply this whole thing by 1, but we're going to do it in a special way. So this 1 we're going to actually represent as b star minus d star over b star minus d star. And as you can see, this term here is equal to 1 because it's the same thing divided by the same thing. So anything divided by itself is equal to 1, and anything multiplied by 1 is equal to itself. So this equation here is the same thing as this equation here. They're functionally equivalent, but it's going to allow us to simplify in the end. It doesn't look like we're simplifying, but we will be simplifying. All right. So the next thing is maybe to write out, we'll just move this b minus d over b minus d, this 1. We're going to move it around to the other side so it'll be more obvious what we're doing. So now we have, this is the most complex thing we're going to write out, and then we're going to simplify after that. All right, so what we have is b star minus d star over b star minus d star. That's taken from here. This is just equal to 1, right? Times this whole thing here, this equation, b star minus d star minus n times a plus c times n. Oops. That's all times n. All right. So there's our equation. And how does this help us simplify? Well, what we can do is move this denominator, b star minus d star, because this is just multiplied by this whole term here, we can switch this b minus d to this. So we can get rid of this here and just divide this whole term by b star minus d star. And if we put that in parenthesis, what we can do is actually divide this term by b star minus d star and divide this term by b star minus d star. That's the same thing as this whole term divided by b star minus d star. We'll just divide this term and this term by b star minus d star, which gives us this. Delta n is equal to b star minus d star times, because we moved this denominator over here, times b star minus d star over b star minus d star, right? That whole term together minus n times a plus c over b star minus d star, times n. All right. This you can read as all one equation, but this you can really start to see will simplify quite nicely. Let's write it out, and then we can simplify it even more. All right, so we will write it out first. Delta n is equal to b star minus d star, and I'm going to put those in parentheses, times 1. This cancels out, right? B minus D over B minus D is 1. 1 minus n times A plus C over B star minus D star. And then multiply that by n. Now, we're almost there. We have to define a couple things. Remember, R is equal to B minus D, right? And R star, that is the optimal growth rate in the population, R max, is equal to B star minus D star. That's the optimal growth rate in the population. And let's define one more constant. Now, we know that A, C, B star, and D star are constants, right? These are the regression terms. These are the density dependence terms. This is the maximum growth rate in the population. This is the minimum death rate in the population. These are all constants. What can you do if you put a bunch of constants together? Is that also a constant? It is, so we can simplify by making this all into one constant. In fact, what we're going to do is we're going to define a constant that's B star minus D star over A plus C. And we're going to call that equal to a constant, and we're going to name it K. And you guessed it, that is carrying capacity. So carrying capacity is a constant that emerges out of these terms, the growth rate, B and D, and the density dependence terms on both B and D. If you have all that, you actually know what the carrying capacity is going to be. And this is what it is. And so if we use these two simplifications, B star minus D star is equal to R, so we're going to replace that with R max or R star, and we're going to replace this with 1 over K. So this is just reversed. This A plus C is now on the bottom here, on the top here. So these are just reversed. So this is 1 divided by K. So we're going to replace this term, A plus C over B star minus D star. We're going to replace that with 1 over K. And let's see what we come up with. Delta N is equal to R star times 1 minus N divided by K. Right? All times N. And if we want to rearrange this, we can do that in a maybe slightly simpler way, or a way that you might recognize. Delta N is equal to R times N times 1 minus N over K. That is the basic logistic population growth model. And I'll just put in R star. You can say R max or R star. And that is how you can go all the way from modeling these density-dependent growth rates, per capita birth rate and per capita death rate, and just make them both density-dependent. And by doing that, you can derive population growth like this, and this is logistic population growth. It's the logistic population growth model, the second most important model in population ecology. So we'll, in the next bit of the video, I will go over how to model this in Insight Maker, and then I will let you go on your own to answer the questions in Lab 2. All right, what we're going to do now is just to go through the same model we just went through in the whiteboard, but we're going to do it in Insight Maker. And so remember, the model is basically, we're taking the exponential growth model where we have births and deaths, little b and little d, per capita birth rate, per capita death rate, that are now dependent on density. They're density dependent. They become less and less favorable If it's births, the birth rate goes down. If it's deaths, the death rate goes up as the abundance goes up. All right, so as abundance goes up, the population vital rates, the per capita vital rates get less favorable to population growth. So let's first start out by making a population. We'll call it N, and we will make a flow that is big B, that is an inflow that represents births, and an outflow that represents deaths, that is big D. And here, I'll move this all down here because we're going to have to build a lot of elements up above. So I'm going to maybe make this even further down so we have plenty of room to work with. Now the next things we might want to do is just add a couple variables. 2 variables for the per capita vital rates. All right. So the per capita vital rates, little b and little d. And we'll link those up to, there we go, to their appropriate flows. We need an initial starting value. Let's give it 10. It doesn't really matter. What's important is that you construct this model correctly. The numbers that you need to put in, like the initial abundance and the density dependence factors and so on and so forth, they are in the lab instructions, so you should be able to find those relatively easily. I just want to make sure that you know how to put this model together and that it makes sense. So that's what we're doing today. Don't worry about the numbers so much. All right, so now we have these vital rates, and if we put numbers on the vital rates, say 0.3 and 0.4 or something like that. So I have a slightly higher birth rate than I have death rate, and I put the proper equations in. Birth rate is little b per capita rate times abundance, and death rate is little d times abundance. Then we can get exponential growth, right? And here, I'll just get rid of those vital rates, and we can see that we have classic exponential growth. You can even see it better if we change this to, say, 150 and run it again at full speed, and there we go, exponential growth. What we're going to try to do now is to make these rates density dependent, and so let's add some more variables here. So remember, little b and little d are both density dependent now in this new model. And so little b is defined as the maximum birth rate minus a parameter a times density. So we first of all have to link density with these vital rates because both of these are going to be density dependent. All right, so that just visually makes both parameters density dependent, and we'll add a few more variables here. 1, 2, 3, 4. So they all are on top of each other, but there are 4 here. And so I'm going to just assemble them like this. And so the birth rate is defined by, I'm going to call it B max. That's the maximum birth rate, and a parameter A, which is the rate at which birth rate declines with density. And I can link those together now. So that little b is going to be defined by those 2 variables as well as density. So we'll do the same thing with little d. Little d is defined by a minimum death rate, which is the most favorable death rate, d min, and it is also defined by a parameter c, which describes the rate at which the death rate increases with increasing density. And so we can link those together with little d, and we're very close to having a proper logistic population model, logistic growth model. But what we just have to do is to implement the equations for little b and little d. So remember, we're just implementing simple density-dependent relationship. You take, at low densities, the birth rate is its maximum level, and then it goes down with abundance at a rate of A. So you have B max minus A times N, representing the density dependence on birth rate. And we can do the same thing with death rate, where you take this minimum death rate, the most favorable death rate, and then as abundance increases, we increase the death rate according to this rate C. So the equation is D min plus C times N, and we can apply that, and we basically have the model down. We can add slider bars to our heart's content if we would like. I would add slider bars on these parameters if you wanted to play around with the different constants here. These are the constants in the model: the maximum death rate, the parameter A; minimum death rate, the parameter C. I hope I said that right. Maximum birth rate, parameter A; minimum death rate, parameter C. So I'm not going to put slider bars on them right now because you know how to do that. So what I will do is put some parameters on these rates. So I'll say the maximum birth rate is 0.6. I'm just making up numbers. These are not the numbers for the lab, so don't, at least I don't think they are. So don't use them that way. I'm going to just randomly say 0.6, and this is 0.0001. Again, I'm just making random numbers here. So I hope this works out because I didn't test these before. Minimum death rate, I will say, is 0.1, and the death rate's going to go up by a rate of 0.00005. Let's see, how many zeros did I add here? 3 zeros and 4 zeros. Okay, we'll see how that works. So we should have these correctly, and this flow should be the same as it was before, because the total birth rate is just determined by the birth times the abundance. That is the little b times abundance, and total deaths is just the total abundance times the fraction of the population, or the percentage of the population that die, and those are the things that are changing with density now. So we should have everything we need. Now, I'm not going to guarantee that the model is going to run beautifully because I just sort of made up some parameters, but let's see what it looks like. Aha! So we do have some logistic growth going on here, and let's get rid of some of the other constants because we don't need to model those. Let's just look at abundance. It looks like the carrying capacity is around 3,333 in this case. Now, maybe at this point I might want to, see if I can make this grow a little slower. Maybe I want to see a logistic growth curve that kind of slowly gets up to carrying capacity. The way I can do that is just to lower some of these rates here. So maybe I'll make that 0.2 and this 0.05 or something like that. And let's see what happens now. So now it's looking a little more like that S-shaped growth curve. And you'll also know that, or notice that carrying capacity changes as well as the rate that the population's growing. So changing these parameters, and I encourage you to play around with these parameters. Do put slider bars on and just see how both the rate of increase changes, the rate at which the population reaches carrying capacity, as well as carrying capacity itself can change when you change these 4 parameters that are part of this model. And the last point I will make, and we made it much stronger during the whiteboard session earlier, but this is the same model as the logistic growth model we built in class, which just had a single double-headed arrow and that implemented the classic equation of population of logistic population growth, where delta n is equal to R max times n times 1 minus n over k, because as we saw in the whiteboard, you can go through all the math, but when we can derive that equation from just this model where both birth and death are related to density in this simple linear way. Disregard all this mess here, but it's really quite simple. We have this linear relationship. Death rises as density increases, birth rate decreases as density increases, and just by following the math, we get this. So these are the same models. There are two different ways of representing logistic population growth, but they really are the same model. And you can derive carrying capacity as a function of these four variables. And Gotelli shows you how to do that. And I mentioned it in the whiteboard lecture because we saw that carrying capacity is B max minus D min divided by A plus C. So that's where I'm going to stop. Good luck with Lab 2. Let me know if you have any questions. Hope this made sense so far. And good luck.